Hello and welcome to the second and final part of the Archimedes and Circles series here on Mathematical Ramblings. This is the second part of a two-parter, so I highly recommend you watch the first part just for context so you understand what's actually going on in this video. Card will be in the top right. If you haven't seen it, basically what we did is we found an estimate for pi using inscribed polygons in a method similar to what Archimedes did more than 2,000 years ago. But if you've already seen it, then what we're going to do is we'll find a limit for pi. I'll explain exactly what a limit is. We're then going to rearrange this limit from the form n going to infinity to n going to 0. And then we're going to look at why radians are so useful. Quickly, before we move on, if you could hit the subscribe button and the notification bell so you're notified of any of my future videos, that would be greatly appreciated. Thank you. Quickly, we'll recap just in case it's been a while since you saw the previous video. So what we did is we used a circle to find an estimate for pi. We know that the area of a circle is pi r squared, and if we have a unit circle then the radius is 1, and so the area of the circle is pi. Now all we have to do is find a shape that approximates the circle well, and that means we're approximating pi well as well. The idea then was that we use an n-gon, so that's a polygon, a regular polygon with n sides, and it's inscribed, meaning that it's fully contained within the circle. Each of the points on the polygon of the n-gon touch the circumference of the circle exactly. We split this n-gon into n triangles and then found the area of each of those triangles. Fairly easy to do. Again, I recommend you watch the previous video if you want to know exactly how we did this. But the result was that the area of one of these triangles was half sine of 360 over n, where n is the number of sides of this polygon. But that's the area of only one of the triangles, so we multiply this by n to get that the area of the entire polygon is half n sine 360 over n. What we can then do is actually look at the progression from a low number of sided shape to a higher amount. So we have the circle, that's the area of pi. If we have a square, the area is 2, that's quite far off pi. But as we increase from a square to a hexagon to octagon to a decagon, all the way to the enneacontahexagon, the godly 96-sided shape, and this is as far as Archimedes went 2,000 years ago, well, with a 96-sided shape, with an enneacontahexagon, we get an area of about 3.139, and that's honestly not far off the actual area of 3.1415. This is the entire idea of limits. So in sentence form, what we can say is that as the number of sides of this polygon increases, the area of the polygon gets closer to pi, and you can see that quite visually. That polygon is taking up a lot more of the circle with the enneacontahexagon. It honestly looks almost like a circle. And then, of course, as I would explain, the area of the circle is pi because the radius is 1. It's a unit circle. We can write the sentence mathematically like this. If n is the number of sides of the polygon, then as n approaches infinity, the area of the polygon, which is a of n, that approaches pi. So this is just a mathematical representation. This is the whole idea of limits. It's the idea of a variable approaching something, and as that variable, for example, approaches infinity, a function of that variable approaches pi, for example, in this case. So as the number of sides of the polygon approaches infinity, the area of the polygon approaches pi. And there's another way to write this. It's just a different notation. It means exactly the same thing. Pi is equal to the limit as n goes to infinity of a of n. This is not, though, it's important, the same as saying pi is equal to the a of infinity. Pi isn't equal to the area of an infinite-sided shape. The circle isn't an infinite-sided shape. It's a single curved-sided shape. And obviously, if you put infinity into the area of polygon function, it wouldn't make sense. Infinity isn't well defined. It's not actually a number, so it's not the same. But the idea with limits is that if we can get close to infinity, then we can get a good approximation. We get a value, even though it's not quite the same as putting infinity into the original function. So there's a subtle but important distinction between limit as n goes to infinity of a of n and a of infinity. But we know what a of n is, and that's what we worked out in the previous video, so again, recommend you watch it. Card will always be in the top right. And we found that the area of the polygon is half n sine 360 over n, so substituting this into the limit, we get that pi is equal to the limit as n goes to infinity of half n sine 360 over n. What we're then going to do is rearrange this limit. So this limit, it was in this form. So we have a limit where n is getting bigger, where n is approaching infinity. saw for some function f of n. In that previous function it was half n sine 360 over n. But sometimes it's useful if we don't have n approaching infinity, but we instead have n, for example, approaching 0. If we want to do that, well, we have to start, it seems as always, with circles. So if we imagine a circle whose area is 1, it's not a unit circle, the radius isn't 1, but the area of the circle is 1. If we split this circle into some sectors, some slices, we can get a relationship between the number of sectors and the area of each sector, which will be useful. And by the way, each of the sectors is identical. If we say that n is equal to the number of sectors and b is equal to the area of the sectors, then those multiplied together should equal the area of the entire circle. For this reason, we can rearrange bn equals 1 to get b is equal to 1 over n. And that makes sense, because as you increase the area of each sector, the number of sectors will decrease, or vice versa. If we continue to add sectors to the circle and continue slicing it, then it makes sense that each of the sectors will have a smaller area. But we will also see that it seems to be getting smaller and smaller, and it's not going to just sort of stop at like 0.1. It's actually getting closer and closer to 0. And that means that we're actually in a sort of limit situation. What we can say is that as n goes to infinity, as the number of slices, the number of sectors goes to infinity, the area of each sector goes to 0. And we already said that the area of each sector is equal to 1 over n. So you can say that as n goes to infinity, 1 over n goes to 0. We can also say that as 1 over n goes to infinity, n goes to 0. So this is just sort of the reverse, the converse. And that's just by taking the reciprocal on both sides. So, bringing it back to the original function, we have the limit as n goes to infinity of some function f of n. What we can now do might seem random, but you'll see why soon, why this is useful. We replace and substitute n with 1 over n. And that gives us the limit as 1 over n goes to infinity of f of 1 over n. And that's equal to the original limit as n goes to infinity of f of n. If we know that as 1 over n goes to infinity, n goes to 0, and that's also part of this limit. Because as 1 over n goes to infinity, n goes to 0, these expressions are identical. They are interchangeable. We can swap them out. We can say that as n goes to 0, 1 over n goes to infinity. So we can switch out the 1 over n going to infinity in the limit for n going to 0. And we'll do that. And that will give us what we actually wanted. So for some function f of n, where n goes to infinity, we can rewrite this in the form of a limit as n goes to 0 as the limit as n goes to 0 of f of 1 over n. So that's how we can rearrange a limit from the form n going to infinity to n going to 0. What we're now going to do is apply this to our original limit for pi. So we found that pi was equal to the limit as n goes to infinity of half n sine 360 over n. I'll put in the implicit multiplication explicitly, just so it's clearer when we do substitution. This form in the top right is what we found for how we can change where n is going to in the limits. What we then need to do is substitute n for 1 over n within the limit. And that gives us, if we use in simplification, 1 over 2n times sine 360 over n, or even in a better form, sine 360n over 2n. So in full, pi is equal to the limit as n goes to 0 of sine 360n all over 2n. And that gives us something. It's a better form of the limit, but it's not its final form yet. What we're now going to look at is a very powerful form of angle measurement. So most people are used to degrees, 360 degrees if you go around a full circle, 180 degrees is a half circle, etc. But there's another form of more useful angle measurement. It's not gradients, it's radians. And it's this. If we imagine a sector, so a slice of the circle, where the arc length, so that's this highlighted purple arc length, that is equal to the radius 2. And the angle formed at the centre for this sector, that is known as a single radian. And you might be wondering, surely this is as arbitrary as 360 degrees. Well, actually no, it's actually really useful, and it has some interesting properties that are useful in calculus, and also for finding a limit for pi, it turns out, which we'll look at a bit more later on in a couple of slides. But if we want to be able to use radians, we need to be able to convert between the radians and the degrees, because our original limit is in terms of degrees for the angles. So we know that the circumference of a circle is pi d, but it's also 2 pi r because there are 2 radiuses in the diameter. And that means you expect to have just over 6 radiuses around the circle. So if we do this, we should find that we have just over 6 radiuses around the circle, and we do. But because for each radii around the circle there is 1 radian, we can say that there are also 2 pi radians. Because it takes 360 degrees to go around a full circle, and it also takes 2 pi radians to go around a full circle, 360 degrees is equal to 2 pi radians. So now, using this in our original limit, we get that pi is equal to the limit as n goes to 0 of sine 360n over 2n. That's the original limit we found just a couple slides ago. We can substitute 360 for 2 pi in this limit, and we get that pi is equal to the limit as n goes to 0 of sine 2 pi n radians over 2n. And we finally found the final form, for now, of the limit. So, and finally, we can now see graphically this limit. So we have 2 lines here. The blue one here is y equals pi, and the red curve is y equals sine 2 pi x over 2x. And you can see that at 0, it looks like the red line, the red curve, is exactly touching the blue line, which would imply that at 0, y is equal to pi, even for the red line. However, unfortunately, it's not. As always, there was no hope. It's undefined. It's 0 divided by 0. But if we go slightly left or right of 0, then we'll get a y value which is really close to pi, incredibly close, or it depends how far you go. But if you only go like 0.00001 radians, you're going to get really close to pi. And if you get infinitesimally small, then you get even closer to pi. But this is the problem with limits. You can never actually reach the point you're going. You can never reach infinity. You can normally never reach 0 because it'll be undefined. But you can get incredibly close to it. But anyway, that's just the graphical representation of this limit. What we're now going to do is find the exact same limit in another way. And this is going to showcase one of the many uses for radians. So first, let's seemingly randomly look at these 2 graphs. The blue line is y equals sine of x in degrees. It almost looks like a straight line, but it's not. And the red one is y equals x. Doesn't seem like anything special is happening, does it? But see what happens when you change the angle unit to be degrees, from degrees to radians. Now it looks like something more interesting is going on. If we zoom in, it'll be a bit clearer. So what we can see here is that around x values of 0, the blue and red lines seem to be very close to each other. Or we could say that sine x is approximately equal to x for small values of x. They see that at 0 is obviously touching, sine 0 is equal to 0, so they're touching at 0, but even just like a few, like even up to half a radian to the right or left, the blue and red lines are actually quite close, so that can be quite a good estimate. So the fact that sine x and x are similar for values of x around 0 is really useful. In fact, you can even use it to show the limit that we worked out for pi. So let's do that. The small angle approximation. So technically we can say that sine x in radians is approximately equal to x for small values of x. So that can be positive or negative as long as it's around 0. We want to find a limit for pi. So we can rewrite pi to be 2 pi n over 2n. We're just timesing by 2n on both the denominator and the numerator, so it cancels out and gives us still pi. What we would then want to do is, because we know that sine x is approximately equal to x for small values of x, if we switch out x for 2 pi n, we get that pi is equal to 2 pi n over 2n, which is approximately equal to sine 2 pi n radians over 2n for small values of 2 pi n. Now it's a bit annoying saying small values of 2 pi n. What exactly does that mean? Well, it turns out we can actually remove the 2 pi from that, and that's because when 2 pi n is small, n is also small, because 2 pi n is always bigger than n. 2 pi n is a multiple of n that's larger than 1. So 2 pi n will always be bigger than n, and for that reason, when 2 pi n is small, n is also small. And from this, if pi is approximately equal to sine 2 pi n over 2n in radians, then you can also say pi is equal to the limit as n goes to 0 of sine 2 pi n radians all over 2n. And that's because we know that as you get closer to 0 with the small angle approximation, the approximation becomes better. Obviously at 0 it's perfect, but if you're only like 0.1 radians right or left from 0, then it's a really good approximation. So thank you for watching. Please like, comment, subscribe if you liked it. Thank you very much if you've watched this far through the video. I really do appreciate it. There'll be more content coming fairly soon. I have to stay tuned to see what exactly that will be, but thank you. Like, comment, subscribe, and bye bye.